Okay, I'm very thankful to the organizers that he gave me the chance to deliver this small lecture. Uh, Myself, Dr. Rajendra More from D.B.J College, Department of Physics. Today, we're going to see the paper number 1, unit number 1, and unit number 1 is probability. There are so many topics, but few topics we are going to see here. Random probability theorems, method of counting, and permutations and combinations, and probability distributions. Let us start with the basic fundamental things. What do I mean by probability? If there are several equally likely, mutually exclusive, and collectively exhaustive outcomes of an experiment, the probability of an event E is given by the number of outcomes favorable to the event divided by total number of possible outcomes. This is well-known definition. Students might have seen few say slides initially, but still we are going to just warm up. So these are the fundamental things. What do I mean by random experiment? When there are more than one outcomes of any experiment, and there is no prediction with 100% confidence of a certain and specific outcome, then that is called as the random experiment. The number of outcomes of this random experiment, the set of all these outcomes is called as the sample space. That is, sample space is nothing but the set of all possible outcomes of a random experiment is a sample space. Then what do you mean by sample point? So each member of the sample space is a sample point. And then what is the event? Out of these sample points, if we put some criteria and make a subset, so subset of a sample space is an event. Now, just previously we have seen what is meaning of the exhaustive event, mutually exclusive event, and mutually exclusive and exhaustive event. So some examples and short definitions are given. If the combination of many events form the original sample space or the exhaustive events. For example, if we roll a die, this die has 6 surfaces, there are 6 numbers are ruled on it, 1, 2, 3, 4, 5, 6. So when we roll a die, then any number will come on the top of the top surface. So what these numbers are? 1, 2, 3, 4, 5, and 6. So this is our sample space. S, it is denoted by S. Now out of this sample space, if we say that the odd numbers only, then from this odd numbers are 1, 3, and 5. Suppose even numbers only 2, 4, 6. Suppose some other criteria 3, 4, 5, 6, just like say number greater than 2, etc. Then if we combine all these events E1, E2, E3, and it is denoted by this U, capital U, union, E1 union, E2 union, E3 is nothing but this original sample space is formed there. Okay, so this is called as the union. And then you may say that E1 and E2 are also sufficient and they are also forming our own sample space. Yes. So E1 and E2 are also exhaustive events. But suppose that out of this E1 and E2, suppose someone number is skipped. Suppose one, yes, sir. Sir, yes. Suppose 3 number is not included in this event, E1. Then E1 and E2 will not be exhaustive events. Then we need E3 because it will be compensated here. Okay. So these are exhaustive events. E1, E2, E3 are exhaustive. What do we mean by mutually exclusive events? If two events have no common sample point, then they are called mutually exclusive. The same example we are taking for the die and odd numbers and even numbers. So you see there is no any common point, common sample point, and therefore it is called as the intersection, inverted U. And there is no any common, so E1 intersection E2 is phi, that is called as a not event. Okay. and mutually exclusive and exhaustive events if the union of two or more events for the original sample space and their intersection is phi are the mutually exclusive events. So here these two events for the same die are mutually exclusive because both of these two are forming the original sample space and there is no any common sample point is. So these are the basic points which we have seen. Let us come to our main point, random variable. So what do we mean by random variable? Random variable is a real valued function whose domain is the sample space of the random experiment, and it is denoted by x. It may be capital X or small x. Okay, so it is a real valued function and it can lie within the same sample space of the experiment, random experiment. For example, if we toss two coins or if we toss a coin two times, then what can be the random variable? Head minus tail. Okay, so this random variable x is h minus t. So what are the possible sample points? So these are the sample points, HH, HT, TH and TT. And what is given? The value of the random variable h minus t. So in first case, HH, two H are there is no tail. So 2 minus 0 is 2. In second case, h minus t, that is 1 minus 1 is 0. In third case, 1 minus 1 is 0. You may write it as a minus 1 plus 1. Again, it will be 0. And in the fourth case, there is no head. So 0 minus 2 is minus 2. So if we combine these all, then we get 2, 0 and minus 2. And therefore, this random variable x has these three sample points now. So then the question may be asked on this, and then we can solve it properly. Of course, we are leaving these points slowly, and then we will go towards the same point in detail afterward. Let us take this is the second example. If we roll two dice on which 1 to 6 numbers are there. So if two dice are rolled, then what can be the possibilities? We may say that on first die there is 1, on second die again there is 1, or on first die 1, there will be a 2 on the second die, and so on. Okay. Or it may be possible that on the first die there is 2 and on the second die there is 1. Or it may happen that on the first die there is 4 and on the second die there is 3. So all the possible events, sample points we have taken here, there are about 36. Okay. Now what can be the random variable? It is given in the second block. Sum of the numbers on the dice, that is x is equal to n1 plus n2. Okay. So 1 plus 1 is 2, 1 plus 2 is 3, 1 plus 3 is 4 and so on. Similarly, 3 plus 1 is 4 and so on. So this is now the new sample space for this random variable x. Okay. If you look carefully towards this, then you see that 2 is appearing only once, 12 is appearing only once, 3 2 times, 4 3 times, 5 4 times and so on. Okay. So the question may be asked on this new set of a random variable. Okay. And again, you see, these are also 36. And if you are asked what is the probability of 2, then 1 out of 36, that is 1 by 36. If you are asked probability of 4, then there are 3, because see here, 1 plus 3, 2 plus 2 and 3 plus 1, all these are 4. So anything will do there, and therefore 3 by 36 will be the probability of appearing 4 for this random variable. So we can write the probabilities of all these sample points, and we can see that how this probability is distributed then of this random variable. And that's why here we are saying that random variables and probability distribution. So what kind of probability is distributed? Let us see towards the next. So here these numbers 2, 3, 4, 5, 6, 7 and so on, these numbers we have taken from the previous slide, from this, these numbers we have collected. Okay. And then what is the probability of 2? 1 by 36. 3, it is appearing 2 times, 2 by 36. 4 is appearing 3 times. and so on. These are the probabilities. And these are written like this: P is equal to f of x. We know what is f of x. X is nothing but what? X, n1 plus n2. Okay, so this is called as the also called as the probability distribution function. Okay, now how this is distributed, you see here, this is the graph plotted for the probability distribution. This is plotted in terms of the dots only. See, one is not appearing, so one has the 0, 2 has the probability 1 by 36, 3 has the probability 2 by 36, and so on. For the 7, the probability is 7 by 36, and again it is decreasing. So this is one kind of the distribution which we have represented here. And you may plot as a line, you may plot as a curve, or you may plot as a bars also. But this is the probability distribution. The important care we should take in case of the random variable, when we find the values of the random variables, then probability of all these random variables must be equal to 1. That is, sum is equal to 1. If you add all these numbers, see all the denominators are 36, and add these numbers, you will get 36 by 36. So this is, say, the checkpoint for this. You can check and say that our random variables are correct here. If it is 1, then it is correct. Okay, so this is how the probability is getting distributed. Let us turn towards conditional probability and probability theorem. So what we mean by conditional probability? If you take a certain random experiment, then this random experiment will have certain, say, number of sample points, that is, there will be a sample space. And from this sample space, we can derive number of events by putting different criteria, by putting different conditions. We can put number of events. Okay, and in these events, some number of points will be there. Okay, so what we mean by conditional probability? If we are going to find the probability of certain event which will depend on some other event which has already occurred, then it is called as the conditional probability. That is, probability of one event depends on the event which is already occurred there. That is called as the conditional probability, which here we try to define. If the probability of an event is determined when some event associated with the same sample space has already happened or occurred, is termed as the conditional probability. Now, suppose that in this random experiment, there are n number of sample points in the sample space of that random experiment. And we are taking two events, A and B. Okay, NA is the number of sample points in event A, NB is the number of sample points in event B. Okay, then NAB is the number of sample points corresponding to both A and B occurring simultaneously. That is, these are the members. These number of sample points are the members of A and B simultaneously. Okay. Then according to this information, if we try to find what is the probability that the sample points are occurring in both the events simultaneously, then this is the probability that both A and B will happen is PAB. It is written by PAB. Number of sample points which are common to both, we write this also union. Okay, union divided by total number of sample points. Now, what is the probability that the event A will happen? The number of sample points in event A divided by total number of sample points of the random experiment in its sample space. Okay. Now here, this is the conditional probability. What is? Probability that B will happen when A has occurred. It is written like this: P subscript A and into bracket B. So probability of A, B, C, they get NAB probability. We are going to find in this case probability of event B when event A has already occurred. Okay. Since you think thoroughly regarding this, then the sample space has and is called as the probability theorem is there. And the problem is somewhat complicated, then you can build up the tree diagram, and this tree diagram helps us to solve the examples. We will take one example, current example we will take. So let us try to understand this with the help of figure. This is the figure. Okay, this is some sample space. There are about, I think, 54 sample points shown in terms of the dots. Okay, now this closed curve indicates event A. This closed curve indicates event A. And this another closed curve indicates event B. Okay, so now in this case, these points, these which are out of these two curves are not now in this case here. But see, these 5 sample points are common to both A and B. Okay, these are common to both A and B. And therefore, in just previous, we have written this definition. Probability of B when A has occurred is PAB divided by PA. Okay, the same definition we are writing in terms of this product. PAB is equal to PA multiplied by PAB. I would like to request all the participants that this say formula you should remember, because this formula we will use in solving the examples further. Maybe the notations will be different instead of A and B, but this formula will be required when we solve the examples. So the same notations are there. PAB is nothing but the probability that both A and B will happen. And this P subscript A and B is also written like this. See here, there is vertical line between B and A. Probability of B when A has occurred. Okay. The number of sample points common to both A and B, we write like this. So it is also called as the intersection. Sorry, previously I told you in union intersection. Okay, common to both of these two. And that's why PAB is also P intersection, P of A intersection B. I hope that this symbol we will use further. Okay, PAB is nothing but P of A intersection B. So this is some we try to understand what we mean by conditional probability. Of course, this will be more clear if we take some examples. So let us take this example and it will clear here. 10 cards numbered 1 to 10. Okay, there are cards and on which the numbers are written 1, 2, 3 and so on up to 10. And they are placed in the box, they are mixed thoroughly. And then a card is drawn randomly. From this box, the card is drawn randomly. And it is known, if it is known, that the number on the drawn card is more than 3. Okay, the number on the drawn card is more than 3. Then what is the probability that it is even number? So here, the card more than 3 is the event which has occurred. Okay, and we have to find what is the probability of the number. So let us try to solve. So what is the event A? The number on the card drawn is greater than 3. This event B is the number on the card is even. The number on that card is even. Then we have to find probability of B when A has occurred. So first of all, we will construct our sample space. What is the sample space? The numbers on the cards 1 to 10. This is our main sample space. Okay. Now, occurred event, what it is telling us, the number is greater than 3. So see here, this is the event A, 4, 5, 6 up to 10, greater than 3 are the numbers. This is the sample space of event A. Okay. What is the sample space for B? Even numbers only. 2, 4, 6, 8, and 10. Remember, when we draw the card, the 2 may also be written, drawn, isn't it? So according to given what? These are the even numbers. Now, what are the common in between A and B? What are the common? A intersection B. So if you see both of these two events, then A intersection B are 4, 6, 8, 10, and so on. Let us try to find now the probability. What is the probability of B? These are 5 number and total are 10, 5 by 10. 1 by 2 we can write it also. Then what is PA? Probability of A. There are 7 numbers, 7 members divided by 10. This is, and what is the probability of A intersection B? Common. These are 4 numbers, and so if we substitute these values, as I told you previously, this formula we will use there. Instead of PAB, we can write here P intersection B. So then we simply place the values and we can find the probability of B when A has already occurred. I hope that you understood this problem, and hence the conditional probability might have been cleared, I think. Okay. But let us take somewhat more example, one more example. And of course, we all are suffering from the COVID pandemic, and therefore I have selected the problem on COVID. Okay. So see, what is the problem? Let us try to read first. We'll find by using the tree diagram, as I told you previously. Of COVID test is specified as follow. What is? Of the people having COVID, 90% of the test detects disease, but 10% go undetected. That is, those who are suffering from COVID, and of the people pre of COVID, those who are not suffering from COVID, they also test 90% of the tests are judged COVID-19 negative, but not therefore they are really detected that they are having the. But those who are not COVID positive, but because of some error in the diagnosis, they are detected as, of which only 0.1 of this 0.1%, this is what is given, is happening. Then one person is selected at random. He has given the COVID test, and the pathologist reports him or her as a COVID positive. What is the probability that the person has actually COVID? Now that students may understand what is saying in this example. Suppose our Indian population is 138 crore, then I think not 8, we reach to 1 crore. I think about 3 lakh, etc. we have the COVID positive cases in our India, say suppose until last. So what is said here, we see, out of the people, these are detected, 90% are detected positive, and 10% though they are having COVID but not detected. And the person who are not having COVID, then out of them 99% are detected, okay, they are not having the COVID, but unfortunately this 1% people are COVID as a positive, detected as a COVID positive. And out of this, the person selected randomly and he is reported as a positive, then what is probability that he is really having the COVID positive? So in such a case, if we let us see how the tree diagram is constructed. See here. This is the experiment. Okay. COVID, as he is saying that 0.1% population is COVID positive. So these COVID positive persons are there. Then 99.9% people are not having COVID or are testing. But what is happening in case of these persons? 90% people are detected as a COVID positive. It's okay. 10% people are not detected, though they are having COVID, they are COVID positive, but they are not detected COVID positive. And in the second branch, if you see, 1% people are unfortunately detected as a COVID positive, though they are not suffering from COVID, but they are suffering from, as per the pathology lab. And of course, 99% people they are COVID negative reported. Now, if any person from this is selected, then the pathology lab says that either this or these people are COVID positive. It is reporting. Okay. If he is not actually having COVID positive, still he is detected. Then what we are going to find the probability that he is actually having the COVID positive test. Okay. So if you understand this tree diagram, then we can define different events regarding this. And this is now the solution. Event E. Then he will line out 0.1. Okay. E. So these are 0.01. Okay. Event A is diagnosed as positive. Therefore, object E, probability of A has probability of A when he has occurred. And these are 90%. If you see in the previous slides, 90% means point. Okay. Now, event E dash. The person selected is not COVID positive. It is not having COVID positive. Then, what is the probability of persons? So, such persons you see here, PE dash we are denoting it, 1 minus PE. PE means these persons which are actually having the COVID and remaining are not having the COVID. That is, of course, it will be 99.9%. Of course, that figure is given there, but still we are making this calculation like this. And therefore, probability of E dash when A has already occurred is 1%, that is 0.01. What is? And then, what is the probability E oblique A? As previously I told you that we will use this definition. So, PE multiplied by PA oblique E. That is those persons who are actually having the COVID. Are actually having the COVID, they are detected. Divided by in the previous slide, that person be from the plus. We take the plus because all possible events. Remember that this is the fundamental definition of probability we are using here, and therefore, what is the meaning of this second term in the denominator? This person who are actually not having the COVID, but they are detected. So this is the denominator, all possible events, associated with the experiment which we have considered here. Now all these figures we have calculated already here. So if you substitute all these values, not 1, PAE is a 0.9 and so on. If we substitute these values, then this will be making calculation out of this 0.083. That is when the person is randomly selected and it is reported positive, COVID positive, then probability of such person who is actually having the COVID and reported as a positive is 0.083. That is 8.3%. This example, I think, is matching with our Indian condition, even recent condition. So I hope that you would like this example and understood also. Let us turn towards the next method of counting and permutations and combinations. Let us take a simple example, then we will come to understand what is the meaning of this. Let us ask ourselves, how many two-digit numbers have either 5 or 7 for the tens digit and either 3, 4 or 6 for the unit digits. We are selecting two-digit numbers. Two-digit numbers means we can start from 1, 0, that is 10. 10 to 99, these numbers we are going to select. Okay. And then after 09 is the two-digit number, it is one number. So unit position, there are either 3 or 4 or 6, and at the tens 5 or 7. So if we start counting, then 53, 54, 56, that is tens 5 and units 3, 4, 6, or 7, 73, 74, 76, that is tens 7 and units 3, 4, 6. So these numbers we will select. So here in say actual procedure, you may say that we count, find the start from 10 to 99, and these numbers we will select. But here, if we apply some principles, then we can find quickly these numbers satisfying these conditions. Okay. So two rows correspond to the two choices of tens digit, and 3 columns corresponding to the 3 choices of units digit. So this is an example of fundamental principle of counting. We will take more detailed examples that you will come to understand. And again, there can be various situations in which such was easy. Let us proceed further. So actually, this is the definition, methods of counting and so on. If one thing can be done in one ways, certain experiment is there, or something you can do in N1 ways. After that, second thing can be done in N2 ways. The two things can be done in succession in that order of N1 multiplied by N2 ways. If again you are third thing can be done in extended for n things for n ways. Got it? So what is actually the meaning of this? Suppose let us take this example for the permutations also. If you are having 3 posts and 3 persons, all the persons are eligible for all the 3 posts. So in how many number of ways you can arrange these 3 persons in these 3 posts? So you can make the calculation. That is when the first person is kept to post number 1, and for post number 2 and 3, the possible, or this is also possible. So anything can happen. And then here taking this example of the chairs, that is called as the permutation. This regards with, so the permutations of n persons with n pairs is denoted, this P stands for permutation. P sometimes it is denoted by probability also. PNN. It is not, extremely sorry, small p also. It is given by Pn is equal to n factorial. How? See here, P n minus 1 multiply by n minus 2 dash dash. Okay, if I expand this, then it will be minus n and plus 1. Minus n plus 1 will be there. It will be this. Okay, and this is n factorial. This is coming to n factorial. You can take the small example and you can make the calculations. You will see that it will be n factorial. Then maybe of different way. Previous slide we have seen that n chairs and n persons, but if we are having arrange only 3 persons, so remaining 7 persons will be without chair. So what happens in this case? What happens? That is 10 minus 3, 7. What happens about n minus 3? So here we are trying to explain it. If the number of chairs are is less than n, where n is less than, of course it is here, then the permutations will be how in different ways. So in that case now, the permutations P will be equal to PNR. In the previous case it was PNN, but now this R is different. Of course we will apply the same n minus 1, n minus 2 dash dash up to n minus R plus 1. Here if I put this into the bracket, then n minus R minus 1. Okay, so that this is the equation number 1. If you remember, this is slide number 16. This equation we will use further. Now just a small manipulation is done in this case. P and R is equal to, of course these terms are drawn below, and n minus R factorial is multiplied and divided to the last term. If you make this calculation, okay, if you make, you can take a small number n is equal to say 4, R is equal to 3, and put here, you will come to know that it is nothing but n factorial divided by n minus R factorial. So permutations P and R is equal to n factorial divided by n minus R factorial. This equation also you have to remember, because this is also used in the further. And as previously just I asked you, what happens about the remaining people, n minus R people, n minus R people. Here, I would like to say that when you arrange 3 persons in 3 chairs in one way, and when some other combination of 3 persons in 3 chairs in other way, in this process, in other side, you are going to arrange these remaining persons ultimately. Because when you arrange these 3 persons in different ways, means you are going to arrange these 7 persons in different ways, in different ways without chair. So that I would like to say here, if we say that the example, suppose there is a housing society and a committee of R people, this example, numerical example also we are going to take. R people is to be formed out of n, here n is greater than, then what are the possible ways in that case? This is very similar like this. Okay, that is this statement is nothing but the summary of this. And here that example that we are going to prove here, what could happen in that case? Then there are different combinations. Okay, when R people out of n are selected for R posts, that is chair, then there are permutations PRR, and of course in the previous example we have slide we have taken, so equation number 1, it is R factorial. And then there can be different combinations C between n and R, because see, if 3 chairs are there and for these 3 chairs you are selecting 3 persons, then what happens about the remaining 7 persons? That is, you are going to arrange all these 10 persons with these 3 chairs. Okay, and therefore once you take them, there are different combinations. This may be the possibility, this may be the possibility. So these possibilities we are going to consider here, and thus the permutations P and R will be then PRR. Of course we know this, Then what will be the combinations P, C and R? Of course, this we want to know. So CNR will be this, that is this term we will transfer on this side. So thus the number of combinations CNR of n things R at a time is given by using that previously equation 1 as well as equation 2. Okay, now second equation, there we have not numbered it. This is our second equation. So CNR will be equal to PNR divided by PRR. So PNR in question 1 we have written n factorial divided by n minus r factorial, and PRR, this we have obtained here r factorial. So these are the combinations. So that previous equation 1 and this equation 2 are very important, and we should remember that when we arrange certain persons for certain pairs, that is 3%, make this arrangement. In other side, we are making the arrangement of the 7 persons without chairs. And that's why CNR is nothing but Cn n minus r. That is 3 chairs or 7 without chairs. Okay, so both of these two combinations will have the same meaning. I hope that our students are understanding what I want to say here. Let us take this example. As I told you previously, we will take the example of this. So a club consists of 50 members, and a committee of president, vice president, secretary, and treasurer is to be formed. In how many ways can a committee of 4 members be chosen? So if you take the reference of previous 2 slides and the equations, then n is given as given 4. So we are going to find the combination CNR. Now see, this CNR is also written sometimes like this: superscript N C subscript R. Okay, it is written, but of course the finally formula is same. And if we put these values, see here, so 50 C4 means C54 is 50 factorial divided by this. And if you make this calculation here, 46 factorial, and from this 46 factorial will be cancelled out, then 47, 48, 49 and 50 will remain. They are made calculation, and you will find that from 50 members to form the committee of 4 members, how many different ways are possible? See here, 2,30,300. 2,30,300 combinations are possible. So many chances are there. There should not be any problem of forming the committee of a housing society. Okay, let us take this second example. Methods of counting. That previously we have seen that the permutations and combination. This is the example of methods of counting. And these are very simple examples which may be asked in competitive exams also. I am going to fast because the time is remaining very small, and still the large number of slides are remaining there. Topics are also okay. 1, 2, 3, 4, 6 numbers are given to you, 6 digits, and using these digits, how many 6-digit numbers can be generated with the condition repetition of the digit is not allowed and of the digit is allowed. If you try to solve this, let us go fast. So first condition, repetition of the digit is not allowed. What we have done here, the numbers of the digits, locations of the digits are denoted by A, B, C, D, E, F. Okay. When you try to fill the first digit, then as we are having 6 digits, so all the 6 chances are there. That is, here we can use any of the 6 numbers. But when we fill the second digit, once the one digit is filled into A, then that digit is not allowed to repeat here. So we are having only 5 choices. So any number of 5 we can put here. Then for the third digit, only 3 will be available, only 2 will be available, and so on. So this way, these are the different combinations. And then what is the possible ways, number of possible ways? 6 multiplied by 5 multiplied by 3 multiplied, and so on. It is a 6 factorial. That is, it is 720. So this is very similar like this. Permutations, n is equal to n factorial. This is when the repetition of the digit is not allowed. In the second case, if the repetition of the digits is allowed, then see, when we fill first digit, 6 chances are there. When we fill second digit, of course, again 6 chances are available because repetition is allowed. That is, say, if you fill first digit A as a 5, then we are allowed to fill B as a 5 also because repetition is allowed. So in this way, for the third digit 6 and so on. So all the possible combinations are there. So what are the number of possible ways? 6 multiplied by 6, that is 6 raised to 6. So if repetition is allowed, then 46,656 number of ways or number of 6-digit numbers can be generated. But if the repetition is not allowed, then only 720. See what is the difference between these two. So lucky draw numbers are on this. This is only the example for our students to do the homework. Homework. It is a telecom company reserves its phone numbers starting with 98. We know that various companies have their phone number starting with 94, 91 and so on, 99 etc. How many 10-digit phone numbers can be generated from the given set of these numbers? Of course, because phone numbers can be any combinations of these digits. Here repetition is, but out of 10 these two are fixed, they are locked. Here we can do nothing. Out of 10, then only 8 numbers we have to fill any of this. So my students will start be solving this. Now let us come, as I told you, the random variables. So random variable again is defined is a real valued function whose domain is a sample space of the random experiment. These random variables are of two types: discrete random variable and continuous random variable. What is the difference between these? These discrete random variables are obtained by counting because they are randomly distributed and therefore we can count them. But continuous random variables cannot be counted. They can be measured. They can be measured. Okay. So discrete random variables are finite in number, but large in numbers, the continuous random variables. Okay. Examples are taken. Number of students in the class we can count. Number of marbles in the jar given, we can count. Or in the institution, educational institution, so heights may vary with the fraction also. So how can we make it? So we can just make the groups of these. Just like we can count how many number of benches in the college we can count. Okay. But in other sense, if we take certain weight and how many number of weights are there, we can't count this. We have to measure either 1 kg, 2 kg and so on. So these are the continuous and discrete random variables. And then how the probability is distributed. Regarding these random variables, probability distribution, here there is a set or the frequency of all the possible outcomes of the random experiment in a random variable in a random experiment is the probability distribution. I am taking this simple example, probability distribution of the numbers on a die. There are 6 numbers, 1, 2, 3, 6, and each number has the probability 1 by 6. So if these are the number that is random variable x, then what are their probabilities? 1 by 6, 1 by 6 all. Okay. And therefore, the probability is constant here. Distribution is constant because every number has a probability. And remember, this again the criteria, our total must be 1 for this. Total 1. Okay. Let us take the second example. In this case, also we in last time. Okay, this is only the repetition of the terms. But this distribution, this, as I told you, of the bar also. So this you see. Okay. So this such type of graph is the discrete distribution of the probability. Discrete distribution. And if I say that here, if I draw this bar, then this is the probability. If I divide this bar into 2, then here it is shown here. So the bars are made smaller and smaller, smaller and smaller. That is, you may say that this bar can be made in terms of a single line. That is, here this blue curve is the locus of all those points which are satisfying this probability. each and every point, and therefore such a probability is called as the distribution is called as the continuous distribution. And this type of distribution is called as a bell-shaped curve. It is a bell-shaped curve of the probability. But remember, the area under the complete curve is always 100% probability, that is, it is 1, always. But if you are asked, what is the probability below this bar? If I am able to draw, or what is the probability below this bar? So area of this bar will be the probability of that corresponding random variable. Okay, so here number of probabilities we can find by finding the number of areas, different areas of the different bars. I hope that you are understanding. Let us take this example, how the probability is getting distributed. Again, there is a defined, but let us take this example. Let us look at the experiment by selecting the family out of 10 families which are denoted by F1, F2 up to F10. And these families are having the family members 3, 4, 3, 4, 2, 4, 5, etc. These are the family members. Then each family, of course, it is equally likely to be selected. Let us select a family and note down the number of members in the family. Of course, it is given, but we are going to select the family randomly and try to design the random variable. So what kind of distribution is there? Let us going to find. If first family is selected, F1, then it has 3 members. See here, 3 members are there. So that random variable will be 3. If suppose fifth family is selected, then random variable will be 5, and so on. All the families we have written there. What are the probabilities of this? If you remember these numbers, some numbers are repeated here. So if the first family is selected, that is if x is equal to 2. Of course, I am taking this in ascending order. So first is 2. 2 means this random variable. Then F4 will be selected. This is this. Okay. So probability of F4 is nothing but probability of random variable x is equal to 2. It is 1 by 10 because out of 10 it is only 1 member. But if x is equal to 3, then 3 members are in these 3 families, F1, F3, F7. See here, this. And therefore this probability will be 3 by 10. For x is equal to 4, 3 by 10. For x is equal to 5, 2 by 10. For x is equal to 6, 1 by 10. So these are the different values of the random variables, and these are indicating that how the probability is distributed. And this is the discrete distribution. Okay. So such description giving the values of the random variables along the corresponding probabilities is called as the probability distribution of the random variable x. This, of course, we have taken from the reference book. Our reference book. I hope that everybody is having this. So if I'm allowed, I'm going to skip because only 6 minutes are remaining there, and students can read this from the reference book. Let us turn towards the probability distribution once again. We have repeated that random variable. Now probability distribution. So probability distributions are classified according to the random variables. Okay, there are mainly 2 types. Just previously we have seen. Then this distribution has different types: binomial distribution, Poisson's distribution, rectangular distribution. There are so many, about 30 types of distributions are there. But in our syllabus, only this: for continuous distribution, normal or Gaussian distribution, and for discrete distribution, binomial and Poisson's distributions are there. These are out of our syllabus, but 3 types of each I am trying to give, and therefore we are having only importance of this first and this 2 in our syllabus. And then what are the distribution functions? Because probabilities are distributed according to the function of the given random variable. So there are different types. So probability mass function, this we are not studying because it is not included in our syllabus. But cumulative distribution, CDF, cumulative distribution function, and probability distribution function, PDF, are there. These 2 we are going to study. Of course, the time will not be available that much. PMF, that is a probability mass function, is used for the discrete variables, but CDF and PDF are used for discrete as well as continuous variables. That's why these are important. In both the cases, we can use them. So let us see the example of this. PDF. We are going to see probability distribution function PDF. It is the function of a continuous random variable whose integral across an interval gives the probability that the value of the variable lies within the same interval. See, in the example, you may have the large range, but out of this large, if you are asked to find what is the probability of this range from A to B, then this is the formula for this. Probability A less than or equal to X less than or equal to B is equal to integration, because this is the for the continuous it is shown fx dx. This will be the formula given for that random variable, and this will be the area under that f of x from A to B. That will be the probability. What are the probability properties of this? F of x greater than or equal to 0 for all possible intervals of x. Okay, and if you are given the certain range, okay, and if this is only the range of the whole example, then it will definitely be equal to 1. Okay, and of course the probability distribution function is 0 outside the given range, because we know we have no any job with it. Okay, then CDF, cumulative distribution function. Cumulative distribution function. CDF of a random variable is defined as the probability that the random variable x takes the values less than or equal to x. Okay, so all these are added there. CDF is equal to x equal to probability that x is less than or equal to x. That is all are added there. Since f of x is equal to probability x less than x, this is our random variable and this is the value of that random variable. So its value is always between 0 and 1. Okay, because we take adding all these probabilities, we are going to add there. So it is ranging from 0 to 1. Okay, from minus infinity to 1, this will be the property of this. Okay, f of x x1 is less than f of x x2. This will happen if x1 is less than or equal to x2, and it is non-decreasing function. Non-decreasing means it is increasing function. Probability distribution function is always increasing function. Let us take the example here. So if you see this yellow diagram, then this is the probability distribution function, and this graph is the cumulative distribution function. That is, all the probabilities are added in the next one. Okay, and that's why cumulative distribution function takes the form of, that is, it resembles staircase. Okay, so this is the function given to you. Within this range, this probability minus infinity to x1 from this to this, and this xi from this to this. Okay, x1 to x2, and it will be x1 to infinity, that is this. Okay, so this is our probability distribution function. Let us go fast. This, as I told you, that all these, for the same example, all these probabilities of the random variable, see, 1 by 6, 1 by 6. So this is the constant. Same example we are going to use for the dart, that for all distribution function is same. But if we calculate the cumulative distribution function, then you see here, it is denoted by small f of x. It is df of x by dx. Of course, it has the proof. I'm not going to take because the time is over. Probability x is equal to 0 is equal to 0 because only these are the numbers. X is equal to 1, 0 plus 1 by 6. X is equal to 2, then P1 plus P2 we will take 2 by 6. If 3, then this 2 by 6 plus 1 by 6, 3 by 6, and so on. So this cumulative distribution function is going on increasing continuously, and last value will be always 1, never greater than 1. And it is plotted here. For 1 it is 0, for 2 it is 1 by 6, for 3 it is 1 by 6 plus 1 by 6, 2 by 6, plus 3, for 3 it is 2 by 6 plus 1 by 6, that is 3 by 6. For 4 it is 4 by 6, 5 by 6, 6 by 6 means 1. Okay, so this is the example of cumulative distribution. Sir, is there the over time? Let us take this example. Only 2 slides are remaining.
Yes, yes, sir. गया तुमसे गया.
I can take no.
Yes, yes.
In an experiment, a trial consists of 3 successive tosses of a coin. If we define random variable x as a number of heads appearing in the trials, then determine CDF and take this example. Then 3 coins are tossed. So what are the possibilities? This is our sample space. This is our sample space, and each must have the same probability. That is, each one has the same probability 1/6. Now, number of heads. In the first case, there is 0, and its probability is 1/8. If number of heads is 1, see here, this is 1, this is 1, this is 1. So 3 cases are there, okay, and 1 head is there, therefore 3/8. If 2 heads, that is here 2, in this case also there are 2, in this case also there are 2, and these are 3 cases, so 3/8. And all the 3 heads, it is 1/8. Okay, so this is our random variable now, 0, 1, 2, 3. And what is the probability? 1/8, 3/8, and 3/8, and 1/8. Now, if we plot the probability distribution, then this. For 1/8, this is the probability. This may not be up to the scale, but try to understand. For one head, this is 3/8. For 2 heads also it is 3/8, but all the 3 heads it is again 1/8. So this is our probability distribution function. Okay. If we are asked to calculate the cumulative distribution, then this we are going to take. We are going to add, cumulate. P0, of course, it is 1/8. Okay. Then what is P1? 1/8 plus 3/8, 4/8. See here, this now made calculation. This is 4/8. Then for 2, P0 plus P1 plus P2, 7/8. And for P3, P0 plus P1 plus P2 plus P3, all are added, 8/8, that is 1. So if we try to plot, then this is 1/8, then 4/8, these are added, then 7/8, and finally it will be 8/8. Okay, so 8/8 means 1. This is 1 there. Okay, so this is the cumulative distribution function. I hope that, sir, I have overed here.
Thank you, sir.
And student might have got some light from my dim explanation. Thank you very much.